Hello guys, so in this video we will have just a quick overview on nucleophilic substitution mechanisms. We know that we have two general mechanisms in nucleophilic substitution. We have the SN1 and we have the SN2. This is like a simple comparison between both just to give you a quick overview. So SN1, that's a unimolecular mechanism. And that's because your rate of reaction only relies on the substrates. So any change in the nucleophilic concentration will not be reflected on the rate. So if you double the nucleophile concentration, the rate remains the same. If you half it, the rate remains the same. But if you touch the substrate concentration, the rate will be immediately changing according to what you do here. So if you multiply the concentration of the substrate by 2, rate will be doubled. If you half it, rate will be halved. In comparison to SN2, which is a bimolecular reaction, that's because your rate relies on both the substrate and the nucleophile. So any change in either of these two concentrations, then you will have a change in the rate. So if you double the substrate concentration, the rate doubles. If you double the nucleophile concentration, the rate doubles, and another way around too. SN1 is a two-step mechanism, or you can call it a multi-step reaction because it happens over two steps, or as well sometimes you will see this, it's a step-wise mechanism. One thing happens at a time. A leaving group leaves first, a carbocation forms, then the nucleophile comes to attack. In SN2, it's a one-step reaction. It's called concerted. Everything happens in one go. In SN1, you're just looking for a weak nucleophile. The most common nucleophiles used are neutral nucleophiles, like H2O or ROH. Those are the most common nucleophiles used in SN1 mechanisms, any alcohols and water. On the other hand, in SN2, we have the nucleophile that starts the reaction. It has to be strong because it attacks the substrate, kicks out the leaving group, and makes a bond to the substrate. So it does two jobs: attack the substrate, and kicks out the leaving group. It's a backside attack. So normally we're looking for anions or strong nitrogen or sulfur-based nucleophiles. The most commonly used nucleophiles are CN-, N3-, amines, thiols, RO-, carboxylates, or RS-. The substrate, which is the electrophile, the carbon with the leaving group, we call it the substrate. The substitution at the center of reactivity. Tertiary is very, very good for SN1. And then followed by secondary. Primary is very rare. It does happen in very special cases if the primary carbocation will be extra stabilized by resonance. So in SN2, we're looking for a methyl group that will be super fast, a primary carbon that's a perfect, secondary carbon that can be okay too. Tertiary, very unlikely to have an SN2 reaction on a tertiary carbon because it's too crowded. In SN1, we have, in stereochemistry, we have a loss of configuration. If you have stereochemistry in their substrate before the reaction, once the leaving group leaves, you will have a carbocation. This carbocation is going to be trigonoplanar. You will have two attacks, top and bottom. You will end up with a racemic mixture. So you end up, for example, you end up with an R and S. So you don't have a specific configuration. That's why we say it's a loss of configuration. For SN2, we have inversion. So if you start with an R, you're going to end up with an S. If you start with an S, you will have an R in the product. Let's now compare energy diagrams for both SN1 and SN2. Sorry, for SN2, this is how the energy diagram looks like. This is for SN2. It's a one-step reaction. Everything happens in one go. Reactants are here. Then you have activation energy to get the transition states, no intermediates, then you go to products. You have the reaction coordinate and you have the energy here. On the other hand, for SN1, you have here, first the reactants together, you spend energy, for the leaving group to leave, you have a transition state. For the leaving group when it leaves slowly. Then you have an intermediate, which is your carbocation. Then you spend more energy for the nucleophile to attack the intermediate, and then you have products. So you have two transition states and one intermediate for SN1. In SN2, you only have a one transition state and no intermediates. Remember one thing very, very importantly, especially in true and false, a transition state is not an intermediate. A transition state is not a carbocation. A carbocation is an intermediate. That's true. So I is the intermediate, which is the carbocation. TS means transition state. EA, which is the activation energy. Couple of terminologies that we mentioned. Racemic mixture. Let's just go over that very quickly. Racemic mixture means 50-50% mixture of enantiomers, 1-to-1 ratio. That's what racemic mixture means. Substrate substitution. The first one, when you have the carbon that's connected to the leaving group, it's not connected to any R groups. This is called a methyl. It's not even a primary. Once you have a 1R group connected to the carbon with the leaving group, this is a primary. When you have 2R groups, now this is a secondary. When you have 3R groups, this is tertiary. Remember something very important you have to be aware of. The carbocation stability. Tertiary carbocations are much more stable than secondary, which are way more stable than primary carbocations. This is because of hyperconjugation. Hyperconjugation. What is hyperconjugation? It's the carbon-hydrogen sigma bond donation into the empty p orbital on the carbon. So when that leaving group leaves, you will have a positive charge here on a p orbital. That will be called the empty p orbital with a positive charge. Every carbon hydrogen in this CH3 has a sigma bond. Every carbon hydrogen sigma bond donates electrons temporary to the positive charge here to stabilize it. So every and here and there. So for these three have 9 carbon hydrogen sigma bonds. Here you have 6 carbon hydrogen sigma bonds. Here you have just 3 carbon hydrogen sigma bonds. Here you have none. So primary is only stabilized by 3 carbon hydrogen sigma bonds. Secondary stabilized by 6 carbon hydrogen sigma bonds. Tertiary stabilized by 9 carbon hydrogen sigma bonds. So the more the better. That's why a tertiary way more stable than secondary, more stable than primary. Lastly, we're going to be looking at the factors that affect the nucleophile. We can have a bad and a strong nucleophile, a weak and a strong, bad and good nucleophiles. Things that affect the nucleophilicity are charge. Any negative charge on the nucleophile, it's much more stronger than its neutral form. So RO minus versus ROH, OH minus versus H2O, RS minus versus RSH. Electronegativity. CH3 minus, OH minus, F minus, fluorine is the one that has the highest electronegativity. Think about it. What is nucleophilicity? It's the ability of a species to give up electrons to its reaction partner, which is the electrophile, to make a bond. Who's more willing to lose electrons and making a bond? Something more electronegative or something less electronegative? So that's why this is more nucleophilic than this. Resonance. You want your charge to be localized, not going anywhere, just ready to go on attack. Not involved in resonance, because this can just resonate like this. So we call it delocalized charge. This is like diluted. It's not focused. It's actually everywhere, distracted by resonance. You don't want your nucleophile to be distracted. So this will be a stronger nucleophile than this one. Sterics. You want your nucleophile to be small and sneaky so it can just be able to go and do an attack very easy. A carbon with an O minus, that's a nucleophilic part, carrying 3 hydrogens, versus carbon with an O-, that's the nucleophilic part, carrying 3 R groups. This is too heavy to go anywhere, but this one here is very light to go. So this is going to be a much better nucleophile than the T-butoxide. Make sure you always look for the charge, electronegativity, resonance, and sterics, or sometimes polarizability. If you compare like RO- versus RS-, the RS- for sure is much better nucleophile. So if you have this, better nucleophile than this because of polarizability, because sulfur is much bigger, so the charge is more distributed, more polarizable, and therefore much stronger nucleophile. I hope that was helpful. Thanks for watching. See you in more videos.